So as per the stability of alkenes, you can also compare the heat of hydrogenation, right? More is the heat of hydrogenation, less is the stability. Everyone?
Yes.
Just like heat of hydrogenation, you can also compare heat of combustion. So the questions are usually asked whenever you have alkenes. They may ask what is the order of heat of combustion. We know that combustion is also exothermic, right? Hydrogenation is also exothermic. Combustion is also exothermic. Whenever they're asking us to compare heats of combustion or heat of hydrogenation, they're asking us to compare the magnitude. So heat of combustion, first I can say it is directly proportional to number of carbon atoms. Just like heat of hydrogenation will be directly proportional to number of pi bonds. Pi bonds being same, then you need to look at the stability of the alkene. Okay. Similarly, heat of combustion will be directly proportional to number of carbon atoms, because during combustion, we are converting the entire molecule into CO2 and H2O. More are the number of carbon atoms, more are the number of CO2 or H2O formed. Accordingly, you will have greater heat of combustion or greater energy released in the process. Number of carbon atoms being same, you need to look for the stability. Okay. Again, more the stability, less is the heat of combustion. Can I say that? Because already the molecule has been stabilized. So its energy is already at a lesser level or at a lower level. Whenever it is converting from that lower level into CO2 and H2O, lesser amount is going to be released. Can I say that, everyone?
Yes, sir.
Okay, so heat of combustion will be inversely proportional to stability, just like heat of hydrogenation. Inversely proportional to stability. Similarly, I can mark for heat of hydrogenation.
Is it, sir? Is it something with pi bond?
Yes, hydrogenation is dependent on pi bonds first. Greater the number of pi bonds, more will be the heat of hydrogenation of that compound. So it is initially directly proportional to number of pi bonds. Number of pi bonds being same, it will be proportional to or inversely proportional to stability, right? More stable the alkene, already its energy is at a lesser level or a lower level. Whenever it is converting into more stable alkane, the energy gap is going to be lower. Agreed? Everyone, I hope this is clear. Similarly, the other thing they may ask is heat of formation. Either they ask a heat of combustion comparison, heat of hydrogenation comparison, or they may ask heat of formation comparison. What is meant by heat of formation? It is the amount of heat released or absorbed when 1 mole of a compound is formed from its constituent elements taken in their standard form, right? So more is the stability of the molecule, more will be the heat of formation. Can I say that?
Yes, sir.
Okay. So with respect to heat of formation, it is directly proportional to stability. Okay. Whatever the compound it is getting formed, if you are having more stability, greater energy is going to be released during the formation of it. So in order to break it, I have to supply the same amount of energy to break it. Okay. So heat of formation is directly proportional to, again, first of all, it is proportional to number of atoms. More are the atoms, more are the bonds that are going to be formed, right? So number of atoms in a molecule, number of atoms being same, or to compare among isomers, you need to compare based on the stability of the isomers. More is the stability, more is the heat of formation. Okay, so if you are having greater number of branches, more is the heat of formation. Can I say that? Because if you have branches, it is more stable. That's what we have read. Agreed, everyone?
Yes, sir. Yes, sir.
Okay,
Yes, sir.
fine. I'll give you some questions. Please mark the answers for all of them.
Sir, can we say like heat of combustion is directly proportional to heat of hydrogenation is inversely proportional to heat of formation?
Yes, yes, you can say that. You can say all those things. Yes, mathematically, whatever you said, it will hold.
Okay, sir.
Everyone, you need to compare the order of stability. Okay, once you know the order of stability, heat of combustion things, other things you can compare, right? So compare the order of stability of these compounds.
Sir, as number of branches increases, can you just repeat what you said?
As the number of branches increases, the stability increases. Right, everyone? As the number of branches increases, stability increases.
Okay, sir. Thank you.
What is the first compound? Is it cis or trans?
It's cis, sir.
Yes.
It's cis, right? The second compound?
Trans.
Trans.
Trans. Yes, what is the order of stability among these two?
Trans is greater than
Trans
cis.
greater than cis. Cis is greater than trans.
Cis is greater than trans in this case, everyone. In general, it is trans greater than cis. I'm giving you a specific example where cis is becoming more stable than trans. It's not necessary always trans should be more stable. If you see here, you have two CS3 on the same side. Here C2H5 is on the same side with CS3. This is bulkier, right?
Yes, sir.
That being bulkier, you have more steric strain or steric hindrance in this particular configuration rather than this configuration. You have CS3 and CS3. This is relatively less steric repulsion when compared to this. Hence, this becomes more stable. If this is more stable, accordingly, you can compare heat of combustion and all those things, hydrogenation, etc. This is the stability order. Is this clear?
Yes, sir.
Yes, sir.
Okay, next example, next question. Mark the order of stabilities of all these compounds. First, I will mark the questions. You try to get the answers. We'll discuss towards the end.
So we have to compare stability, right?
Yes, you need to compare the stability. Everyone just give an attempt, I will explain. You may also have to consider the ring strain. Whenever you have ring compounds, you have to consider the ring strain. We understood that cyclopropane has highest amount of ring strain, right?
So branching show will branching be a more dominating character? I mean, dominating property than ring strain.
I will tell you. First, you get whatever you feel, you take a call. I'll tell you. First, you look for the alpha hydrogens, ring strain, all these conditions. Whatever you feel, you first mark the order. I will tell.
Krishant, என் கிளாஸ் நீ அங்க இருக்கு.
Are you done?
Sir,
Yes.
2 minutes, sir.
So can you give a bit more time?
Yeah. Okay, shall we discuss?
Yes, sir.
Yes. In the first example, if we count the number of alpha hydrogens, this has 2 alpha H. This has 4 alpha H. And the other 2 compounds also has 4 alpha H, right? But here the dominating factor is ring strain, because whenever you have an sp2 hybridized carbon, what is the angle supposed to be?
120 degrees.
Degrees, sir.
120 degrees.
120 degrees, and you are having here 60 degrees. It may not be 60 degrees, there will be due to that strain, there will be a change of the bond angle, but I'm saying it is supposed to be 120, but you are making it 60 degrees, hence there is high angle strain. Here the angle strain is relieved. Here the angle strain is relieved even more. Here there is no angle strain,
So
or
we studied that pentane actually has least amount of deviation, no, sir.
sorry.
So we studied that pent only will have the least amount of like deviation in the previous example that you gave.
For cyclohexane, he says.
That is cyclohexane thing.
Uh,
Alkene.
here we have the ene also. No?
It's alkene also here. In fact, in case of cyclohexane, there is no ring strain only, right? Okay. Cyclohexane has the least deviation, or it has no angle strain because it is 109 in the chair conformer. Remember? But this is the cyclohexene thing. Just let us just say that this has lesser ring strain, and this has even more lesser ring strain. As the number of carbon atoms increase, the ring strain decreases. Okay. So the answer of this is going to be stability order, right? So this is going to be lesser when compared to this, when compared to this. In the next case, all of them are cyclohexene only. You compare here using the alpha hydrogen. In the first case, you have 4 alpha H. Number of alpha H, everyone. In the second case,
7
Seven.
alpha H.
Then 10.
And then you have 10 alpha H. So the order of stability, this less than this. Or in a way, you can say branching is more here.
Sir, can we twist the cyclohexene ring such that the double bond stays with its alignment and the rest of the ring is overlapping on front of it? Like we did for octene in the beginning when we talked about ring strain.
Only you understood whatever you said.
Sir, in beginning of ring strain and octene, you showed a diagram, no, sir?
Yes.
Similarly, can be oriented in the same fashion.
Don't
with
rotate it. We already discussed that you have to, in the isomerism for the cyclic alkenes is possible if and only if you have that octene thing, right?
Okay,
So,
sir.
octene thing, don't rotate it. Okay.
Okay, sir.
Don't complicate our already complicated lives. Okay, everyone. Keep it simple.
Sir,
Yes.
sir, can we say that with the number of resonance contributing structures, the stability also increases?
Hypercon. Yes, yes. Yeah,
Yes, so that can be applied in the first case, right? Not in the second case, but in first case.
in the first, this one,
Yes, sir.
where there is resonance.
Oh, okay. Sorry. Sir. Yes. Okay.
Okay, in this third example. In the third example, what's the answer?
A is
One-
greater than B.
A less than B, sir.
A less than B. Yes. Because in this case, you are having 2 sp2. This is also sp2. This is also sp2. So these bonds are highly strained. In this case, only this is sp2. The other is sp3. The relative strain is lesser in this. It's all relatively. Even sp3 is strained, I understand. But sp2 is more strained, right? This is 109.5 degrees and here it is 60 degrees. Here, both the things are 120 and you are making it as 60. So there is higher strain here when compared to this, hence this is more stable. Again, I'm comparing this based on the strain rather than alpha hydrogens. In case of cyclopropenes or in 3-membered rings, ring strain is the more dominant factor. If you see, look at the number of alpha hydrogens. You have 3 plus 2, I think. You have 5 alpha H, right? You have 5 alpha H, and I think you have only 4 alpha H here. Agreed, everyone?
Yes.
You have only 4 alpha H. Despite having lesser alpha H, this is more stable because of the higher ring strain in this compound. Okay. In this case, you compare using alpha H, you have 2 alpha H, you have 5 alpha H. Ring strain is the same for both of them. So this is stable. Second is more stable. Yes. Next question answer.
Sir, is the first one more stable since ring strain is less significant?
Very good. Very good. That's absolutely right, everyone. The ring strain here becomes less significant because in case of cyclopentene, the ring strain is already relieved. You don't have so much ring strain. Okay. Hence, alpha hydrogens make dominating factor when compared to the ring strain. So count the number of alpha hydrogens. I think you have 7 alpha H. Correct me if I'm wrong, everyone. You have 4 alpha H in this. So here ring strain is relatively less. Ring strain is less dominating factor. Okay, so whenever you have carbon chain greater than or equals to 5, you need not look for the ring strain, you directly look for the number of alpha hydrogens. Okay, yes, the next question.
Sir, A is greater than B.
A is greater than B. Okay. Everyone, that's right. A is greater than B, that's absolutely right. See, what is happening here is this is a continuous conjugating system, right? Okay, here it is like cross conjugation. Either you have conjugation of this pi bond with this or with this. At any instant, it is with this or with this. So such systems are called as cross conjugated systems. So whenever I will write one point here, you need to apply that particular point. When number of conjugated pi electrons are same. So in both the cases, the number of electrons in conjugation are 6 only, right? 6 or yes, 1, 2, 3, 4, 5, 6, 6 electrons. When number of conjugated pi electrons are same, the linear conjugated system or isomers are more stable than cross conjugated structures or isomers. Cross conjugated structures. In this case, at any instant, you have this as the conjugating system. Okay. Or this as the conjugating system. If it is going in conjugation with the left, it may not go in conjugation with the right. If it is going in conjugation with the right, it cannot go in conjugation with the left. Agreed? But here it is continuous conjugation system, pi alternate pi alternate pi. So you can have continuous conjugation. Else if you draw a resonating structure. Everyone with me?
Yes, sir.
Yes.
Yes,
Yeah.
sir.
have pi bond, negative, positive, right? So this positive charge is unable to go in conjugation with this now. But here, whenever you are migrating this, you have positive. That positive charge, whatever is formed, it can again go in conjugation with this. Agreed? There is greater distribution happening. So just apply this whenever you have similar number of pi electrons in conjugation. The linear conjugated systems are always more stable than the cross conjugated systems. Fine. Okay, solve this. I'll give you some set of questions. You attempt all and then we will discuss. Yes, please solve these things.
So what happened, sir?
What happened?
Somebody kept timer?
There's some majestic sound change.
Yes, sir.
Yes, sir.
Yes, sir,
What?
even for me.
Yes, yes, even I got that. But we are placed in different places, no? So no problem, don't worry. Who are the participants? Everyone solve fast. The clock is ticking fast. Okay, answer for the first question.
The first one is more stable, sir.
First one is more stable.
One,
In 1 greater than 2. In this case, even though you have cross conjugation, if you have this extra, see the only difference between these two is you have this as an extra, right? So because of that, you are forming extra resonating structure. You have anyways resonance in this, which is similar to this, but you will be having extra resonance with this. So greater resonating structures will give you greater stability. So here you should not apply that cross conjugation thing. That is applied only if and only if you have same number of pi electrons in conjugation. So this is always more stable than this. In the second one?
The second is
The
more
one is
stable.
more stable, sir.
Second one is more stable. Third one? Third one, everyone fast?
No, I think the first
It's
one
the
is more
first
stable.
one, sir.
Yes, first is more stable. No confusion, everyone. It's a continuous conjugation or linear conjugation. In this case, it is cross conjugation. That's it. This is more stable than this.
So we should only consider the conjugated part, no, sir, not the other parts of the ring.
Yeah, other parts won't be affecting. Other parts won't be affecting. Resonance is more dominating factor when compared to hybrid conjugation. You may feel you have 2 alpha H here, you have
No,
alkenes.
sir, my doubt is that is sp3 hybridized, so it might be lying out of the plane.
Which one?
The carbon beneath the two pi bonds.
Okay, let it be. It
So
was,
that's it.
these are the carbons I am interested in because sp2, 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 sp2. The resonance is in here. Okay.
Understood, sir.
Okay. Shall we go to the next application?
Yes, sir.
Okay. Next, acidic character
Sir,
of
can you wait for a moment, sir?
yes. I'll share it. Everyone, I'll share it post the lecture.
So just to confirm, ring strain is relatively unimportant for 5 or more atoms, right?
Yes, it is relatively unimportant.
Even if the number of common atoms in the ring is very high.
Yes, sir.
Okay.
Yes, yes. Okay. Next application, acidic character of alkenes. Observe here. We already understood that in hyperconjugation, there is delocalization of the sigma bond, because of which if you draw the resonance hybrid, the sigma bond is becoming partial. Agreed? If the bond is becoming partial, the bond energy decreases. If the bond energy decreases, I can break the C bond H whenever you have a stronger base. I can break the C bond H as carbon negative and H positive whenever you are having a stronger base. What do I mean by that? Suppose if you see the acidic strength of, if I want to compare the acidic strength of this alkene and this alkene, the bond I am interested in breaking during the acidic strength comparison is this particular bond. I have CH2, you have bond hydrogen on this. I will be breaking this bond rather than breaking this C bond H. Okay. Reason being, this particular bonds, these three bonds have participated in hyperconjugation with this pi bond. Because of which they have become partial. Once they have become partial, the bond energy got decreased. So if at all I break that bond and I form the conjugate base, the conjugate base is getting resonance stabilized. If you break the other C bond H, let us break the other C bond H. What will you have? You have CS3, CH, double bond, CH. You have negative charge here. This negative charge is present on sp2 hybridized carbon, which you may feel is more electronegative. But once you convert this into carbanion, if it is resonance stabilized carbanion, even this carbon is going to be sp2, right? This is also sp2. So with respect to electronegativity, both of them are equally electronegative. Apart from that, you also have this negative charge distributed in resonance, which is going to form equivalent structures, or in the resonance hybrid, this carbon is going to bear half charge and this carbon is going to bear half charge. Agreed? So which is the better bond to break? The double bonded carbons hydrogen or the single bonded carbons hydrogen?
The single bonded
Single
carbon
bonded
hydrogen.
carbon.
Right, everyone? Okay, so I am breaking that. And we also understood that initially in the overall acidic strength, we have placed the alkanes towards the end. Reason being, C bond H is very less polar, or else in order to break that C bond H, you require very high amount of energy, or a base cannot easily abstract that C bond H. In this case, relative to alkanes, the base can easily abstract this C bond H. It's only relative, okay? Its acidic strength even now is less, but it is not so less when compared to alkanes. This particular part, I can treat this particular part as an alkane part because it is sp3 hybridized, or it is an alkane part. Even though it's an alkane part, its acidic strength is becoming higher when compared to the normal alkane because of hyperconjugation. And in this case, if at all I want to compare out of the two hydrogens, which is more acidic, A will be more acidic when compared to B, because in B, whatever carbanion you are forming, it is being destabilized by plus I effect of two alkyl groups. Here it is being destabilized by plus I effect of only C2H5. If at all they ask us the question to compare among A and B, but in general, A and B are least acidic or they are equivalent to not acidic. But if you break the H positive and you form the carbanion, if at all you want to compare, then you can compare as A is going to be more acidic hydrogen when compared to B. Everyone with me?
Yes.
Yes, sir.
Okay. Now I want you to compare an alkene with an aldehyde or a ketone, an alkene with an aldehyde. Out of these two, which is going to be more acidic?
Ketone, sir.
Ketone, sir.
The ketone or the aldehyde part will be more acidic, right? Because
Yes.
in both the cases, the bond has become partial because of hyperconjugation. There is hyperconjugation happening in both. These C bond H will participate in hyperconjugation and the bonds will become partial in the resonance hybrid. Here also bonds will become partial in the resonance hybrid. So I can break those C bond H and I can form a conjugate base. The conjugate base is more stabilized in the other case. Even though this forms equivalent structure, you will have negative by 2 distribution. In this case, even though there is no negative by 2 distribution, you will have more negative charge distributed on oxygen.
Sir,
And it
is it not CH, not CH2?
yes. I'm sorry. CH negative. We discussed something like this in our one of the lectures. Even though this is an equivalent structure being formed, you need to analyze which is getting more stabilized. The negative charge on more electronegative atom is better stabilized. So rather than distributing the same negative charge half and half on this, you distribute greater than half on this oxygen and less amount of negative charge on this. So this can effectively handle that lesser amount of charge and this can effectively handle that greater amount of charge. Right?
Yes.
So out of aldehydes and alkenes, which are more acidic?
Aldehydes.
Aldehydes. I'm sorry. Aldehydes are more acidic. So whenever you have a base, suppose let us say later on we need to analyze something like this. Whenever you have an alkene and an aldehyde, both of them are present in the same mixture. You are adding a base into it. The base is going to react with aldehyde first. Reason being, this is more acidic when compared to this. Okay. Then accordingly, you need to do some other reactions. But first, the base is going to abstract the acidic hydrogen that is present here rather than abstracting it here. Can I go ahead?
Yes, sir.
Next, stability of carbocations. Stability of carbocation is again compared using hyperconjugation. You are having here in the first case 9 alpha H. You can also compare the stability using plus A effect. Here you are having plus A effect based because of 3 alkyl groups. In the second case, you are having 1 alkyl group, 2 alkyl groups, and in the third case, you have 1 alkyl, there is no alkyl group. Based on inductive effect, I can always say this is more stable when compared to others. But now that we have studied hyperconjugation, and hyperconjugation is a more dominating effect when compared to inductive effect, you need to tell the reason based on hyperconjugation first. You have 6 alpha H, you have 3 alpha H, you have no alpha H here. So the answer is going to be this greater than this, or 3-degree carbocation is more stable when compared to 2-degree, when compared to 1-degree, when compared to methyl. And the reason is, predominant reason is hyperconjugation. Fine, everyone? Let me give you one question here.
Yes, sir.
Okay, before that, a comparison of all effects. Whatever effects we have studied so far, we have studied inductive effect, resonance, as well as hyperconjugation. Inductive effect happens through sigma bonds, or it is sigma-sigma interaction. Resonance happens through pi bonds, it is pi-pi interaction. Hyperconjugation happens between a sigma and pi bond. And most appropriate way of writing this is between sigma and pi star. It's better to write it as pi star, but the interaction is between sigma and pi bond. That's what I wanted to mention here. And in case of inductive effect, there is only shifting of electrons, which is happening through strong sigma bonds. In case of resonance, there is transfer of electrons, which is happening through weak pi bonds. Hence, the transfer is going to be effective. In case of hyperconjugation also, there is transfer of electrons, but it is happening through strong sigma and weak pi. Hence, it is a weaker transfer of electrons when compared to the resonance. So overall order of importance is resonance greater than, hyperconjugation greater than inductive effect. Clear, everyone?
Yes, sir.
Okay, if that is clear, please tell me, out of these two, which is more stable carbocation?
The second one most stable.
Okay, second one. How many of you feel second is more stable? Okay, fine. Everyone please participate. Everyone please put your video on. I think no one has done their video on. You just,
Sir, I think second one is more stable.
yes, second one is more stable. Everyone, that's right. You should not just look for the inductive effect, everyone. Inductive effect is the least dominating effect. So you need to compare the inductive effect only after you are unable to compare using other effects. This is plus I. Yes, this is plus I. This is plus I. OCS3 is minus I group. That's right. But the more dominating factor is resonance. You have a lone pair. They won't show that lone pair and they won't show the resonance in the question paper. You need to understand, yes, there can be resonance inside this. If you form the resonating structure, what's the specialty about the formed structure?
It's octet complete, sir.
Yes, it's octet completed structure. So this is more stable. So the resonance hybrid is going to mimic this structure rather than this structure. Okay. So this is more stabilized by resonance. This is less stabilized by inductive effect, or in fact, you have hyperconjugation too here. Rather than inductive effect, hyperconjugation is even more dominant. You have how many alpha H? You have 6 alpha H. In this case, how many alpha H? You have only 3 alpha H. But resonance is even more dominating when compared to hyperconjugation. Hence, the stability becomes less than this. Okay. Next, you need to compare the stability of alkene. Stability of alkene is compared on the basis of resonance first, then followed by hyperconjugation. So what's the stability order then?
Second is greater, sir.
Second is greater. If you count the number of alpha H, you have 8 alpha H here. Here you have only 1 alpha H. But you have a resonating system, pi alternate pi. And a multiple bond electronegative atom will always pulls the electrons onto itself. So there is resonance here. So because of resonance, you have a greater distribution. I hope every one of you are now more or less comfortable with drawing the resonating structures. You practice all the structures which are already part of the notes. More than sufficient. So there is resonance happening. Hence, this is more stable. So you have 1 to be less stable than 2. Alkenes, stability of alkene. Clear, everyone?
Sir, could you scroll up, sir, a little bit?
Which part?
Yes, sir. That's all. Yes, sir.
I'll send the notes. Once again, I'm telling you, I will be sending the notes. Don't worry.
Yes, sir.
Okay. Then we have something called electromagnetic effect. But before understanding electromagnetic effect, I want to do some more applications of all these effects. One of the most standard questions that is asked is the comparison of dipole moment of different molecules. Everyone, do you remember dipole moment? How is it calculated? Dipole moment mu is equals to, or mu bar is equals to, it's a vector quantity, right? Q into D. And between Q and D, often or in almost all the cases, Q is taken as the dominating factor, unless and until if there is any exception, we will look into it. Q is more dominating factor. So more is the charge, more is the dipole moment in the bond, right?
Yes, sir.
I will directly give you some questions. Will you mark the answers of dipole moment of those compounds? We will discuss whatever knowledge you have. Based on that, try to mark the dipole moment in the bonds shown as well as in the overall compound. The bond shown is usually the dominating bond for the comparison of dipole moment in the overall compound. Mark the questions first, or whatever is there on the screen, you can directly try to apply. Yes, order of dipole moment in these compounds. First, solve these. We'll go to the next set of questions.
Sir, can you go up? I was
Okay.
away for a few minutes, so
Which part?
do you explain the electromagnetic effect?
No, I didn't. I didn't.
Oh, okay, sir. I thought I missed something.
No, I didn't. Order of dipole moment among these compounds. They are arranged in such a way, is it? So you need to just understand if it is greater or lesser. Okay, answers everyone. All these groups, whatever I have attached here, they are minus I groups, right?
Yes, sir.
CS3, there is no bond polarity in there, but all these are minus I,
Yes.
and the order of their minus I think I have marked in the same order. NO2 greater than CN greater than CHO greater than Cl greater than OH, right? So you have greater amount of partial positive charge here, greater amount of partial negative, and the direction of dipole moment is always from positive to negative, right? So it is in this direction, or it is in this direction. So there is some partial positive charge induced on the carbon because of the minus I effect of the groups. So you have the order of dipole moment as this. Agreed?
Yes, sir.
In this case, you have mu equals to 0 because there is no electronegativity difference between any of the carbons. Mu is 0, so this will be lesser. This is sp2 and this is sp. So this is more electronegative, so you have greater partial negative on this, greater partial positive on this. You have relatively less partial negative and less partial positive. So this will be lesser than this. Can I say that? Okay. Again, here also you can compare based on hybridization. This is sp3. This is becoming sp2. This is becoming sp. So the bond polarity in this will be highest because it is not resisting so much whenever it is withdrawing electrons. In this case, even though Cl is more minus I when compared to alkene, net result is this will be withdrawing electrons. Okay, even though this is withdrawing electrons, this is having some resistance when compared to this sp3 hybridized carbon. This has even more resistance when compared to this sp2 hybridized carbon. Agreed?
Yes, sir.
Okay. So the charges induced will be highest here. Always charge is the more dominating factor. So this greater than this greater than this. Bond length also, if you observe, this is only greater because then sp3 hybridized orbital is the larger orbital when compared to sp hybridized orbital, right?
Yes, sir.
Okay. Anyways, you compare only using charge. Charge is the dominating factor. I'll give you an example where the size becomes important. Shall I go to the next set of questions?
Yes, sir.
Okay. Next question. Compare the dipole moment among these HF, HCl, HBr, HI. Then CH3F, CH3Cl, CH3Br, CS3I. This question is very important. It is standard question that is usually asked in mains. Repeat question. Then C2H5F, C2H5Br or Cl first. C2H5Br C2H5I. Yes, solve among these three. Okay, answers everyone.
This
First
is
question. What's the answer?
probably, this is probably wrong, but I got it as increasing for first and decreasing for second two. Sorry, last two.
Okay. And the first one you are saying HF is less than HCl, less than HBr, less than HI.
Yes, sir.
Okay. So in general, we say this statement, hence you might have answered it something like that. In the group, we say size is the dominating factor, and in the period, we say electronegativity is the dominating factor, right? So if you are taking size as the dominating factor, you may see Q into D as distance as the bond length increases, because the size is increasing, bond length increases. You may feel HI should have a greater dipole moment. But as we already mentioned, Q is the dominating factor in almost all the cases. There is only one exception we have. So Q is the dominating factor in almost all the cases. So partial negative charge on fluorine is the highest. So dipole moment is HF only greater than HCl greater than HBr greater than HI. So don't use that logic where we compare size in the group. Dipole moment is overall compared using charge. Charge is the dominating factor, hence follow that. Everyone with me?
Yes.
So in this case,
Yes,
we
sir.
expect, this is the expected order. As per our understanding, this is the expected order. This is the only example where we will be deviating from that particular charge thing. CS3Cl becomes greater. CS3Cl becomes greater because of the bond length. You have charge as well as bond length greater than CS3F. This is experimentally found out data. CS3Cl is greater than, CS3F greater than. The other things are the same. So only between CS3Cl and CS3F, there is an exception happening because of the greater bond length of C bond Cl. Because of greater bond length of C bond Cl, you are having greater dipole moment in the molecule when compared to CS3F. Very, very important. Remember, this is the order. If you have C2H5 and F, if it is not CS3, if it is any other alkyl group, you use the same thing, which is charge as the dominating factor. So here there is no change in the order. The only change happens whenever the alkyl group is CS3. Is this clear?
Yes.
Okay. Remember this. Only exception. We have this as the only exception. Rest all other things you always compare based on the charge. Some other examples, everyone. Again, compare the order of dipole moment among all these molecules. In here, everyone concentrate once. You may say there is some resonance happening, right? Because of resonance, you will again have some partial positive character. Agreed?
Yes, sir.
Okay. But whenever you have halogens, what did we consider? In case of halogens, minus I to be more dominating than plus M, right? So whenever you have halogens, you need not worry about the resonance taking place, which is going to affect the charges. You need not worry about it. Is this okay? Next set of examples. Is it raining at your place?
No, sir,
No.
unfortunately not.
Sir, I think it's stopped. Yes, sir, it's stopped.
Okay. Why unfortunately not? You already have this online lecture, no?
Sir, if it rains today, chance it will rain later in the night.
Okay, okay. I don't think online lecture is bad. It's also good.
No, sir, the issue with online lecture is if it's an offline lecture, I can study properly. If it's a holiday, I can understand properly. Online lecture, I can't do either properly.
You can't do either properly. At least for me, online lecture
The first question was given in the exam, I think.
it is given in the exam.
No, sir, with CN instead of CN.
Yes, yes. I prefer online because I need not ask you people to be quiet. And I can work from home. But not online some days. I prefer offline only because I can interact. Again, you need to compare dipole moment among all these molecules.
Sir, I have a doubt.
Yes.
So when comparing the dipole moment, instead of using electronegative difference, it's better to use plus I effect difference, right? Like
Yes. Yes, yes. In case of organic compounds, you see the electronic effects because dipole moment is the direct application of electronic effects. We
understood.
mentioned a statement, all these can be correlated to dipole moment, something like that, right?
Yes,
So electronic effects plays major role in determination of dipole moment.
got it. Sir.
Yes, please mark the order of dipole moment of all these molecules. Take 5 minutes, we will discuss. Everyone in the lecture?
Yes.
Yes, sir.
Okay, I will randomly call out some names. You just tell me yes, sir. Ritvik Sriram. Ritvik Sriram, are you there in the lecture?
Sir, he is probably talking, but you can't hear him.
But he didn't unmute, no?
Would be a technical.
Could be a technical error. So friendship comes first than anything else. Okay.
So heavier isotopes have greater plus I, right?
Sorry?
Heavier isotopes have greater plus I effect, no?
That's right. That's right.
Thanks.
Sarveshwar.
Yes, sir.
Okay, okay, you are there.
Sir,
Sriram Indian.
Yes, sir.
Okay, you are there. Prinav.
Yes, sir.
Sai Saramati. Sai Saramati, are you there in the lecture? Srinidhi. Yeah.
Present, sir.
Yes, yes. Sayananya.
Yes.
Okay. Where are others? Sanjay.
Good afternoon, sir.
Good afternoon. Good afternoon. Good.
Sir, Hasan, sir.
Hassan. Hassan. Yes, sir. I can't unmute. Fine, fine, Hassan. Hassan, Sriram wanted to check. Okay. Hasila.
Yes, sir.
Okay, okay. Hasila, what's your DP? It's from Harry Potter.
Um.
Okay,
Yes, sir.
okay, okay. Sai Saramati, you are not there in the lecture. Fine. Ritvik Sriram. Sanjana. Yes, you unmuted, but I couldn't hear you. Fine.
Present, sir.
Yes, yes. Everyone done with the questions? Ojas, are you there?
Yes, sir. Yes, sir.
Okay.
I'm done, sir.
Done? Okay. Please answer everyone. First question, answer.
Definitely increase.
First question, you need to basically check between this carbon and Cl bond. So the direction of dipole moment is positive to negative. So you have it in this direction. And for the other bond, you have it in this direction. So both of them are in opposite direction. So mu is going to be 0. Right? In this case, what's the angle between these two?
120 degrees.
The angle is 120 degrees. Mu resultant is mu1 square plus root over mu1 square plus mu2 square plus 2 mu1 mu2 cos theta, right? In this case, what was the angle?
30 degrees. 60 degrees.
60, right? 60 degrees. So this has to be lesser compared to this when compared to this. Agreed?
Yes, sir.
Okay. Here, the direction of dipole moment between C and Cl is towards up, or it is from positive to negative. And this carbon is sp3 hybridized, this is sp2 hybridized. So you'll have partial positive on this, partial negative on this. So the direction of dipole moment of this bond will be towards up, right? In this case, this is towards up and this is pointed in this direction. So there is some angle. Okay, there is some angle, or you have some cancellations also, right? If you resolve that into vectors, so there will be some cancellations. So what will happen? You have this greater than the other. Everyone with me?
Yes, sir.
Okay. When you have NO2, in this case, you can mark NO2 as something like this, as a resonance hybrid, because within NO2 you have some resonance, right? You have negative by 2, negative by 2, and then you have something like this. Agreed? So the resultant will be in this particular direction. Can I say? Everyone?
Yes, sir.
Yes, sir.
Okay. Or in this bond also, this will be in this particular direction. It will be in this direction, and in this bond, this will be in opposite direction. So both of them will be cancelled. In this case, it's only 1 and NO2, so in this direction. In this case, it's towards this. Because of this bond also, it is pointed upwards. Yes. In case of NO2 and OCS3, what do you feel?
So O has a lone pair, sir, and it's nearby a conjugated system. So O's lone pair will try to participate in the conjugation.
Exactly. Everyone, that's right. So because of conjugation, you have partial positive appearing here, negative appearing here. Okay. Or this is oriented in this direction. You have greater and greater negative density concentrated here because this is giving group through resonance. And you have greater positive charge appearing here. If you apply minus I effect, this may seem like greater minus I. So you may feel like positive is here, negative is here. The direction of dipole moment is towards down. If you apply minus I, you may feel this, but this is wrong. Resonance is more dominating for OCS3. Hence, the direction of dipole moment is again placed up. Here it is happening through. Here it is happening through. You can also say hyperconjugation, everyone. Here, you can release electrons into the carbon chain through hyperconjugation, right? Everyone?
Yes, sir.
Yes, sir.
Do you want me to draw the hyperconjugating structure?
No, sir.
No need, sir.
No need. Okay, I will draw one structure anyways. So you can have hyperconjugation, which is also electron releasing. So you have it here, you have it here. So you have a negative charge appearing here, and you can draw those resonating structures. And you have some electron releasing happening through hyperconjugation as well as through inductive effect, but resonance is more dominating, so this will be higher. So the answer for this is going to be, this is least. The first one is least because it is cancelled out. The second one, then there is some addition because of CS3. There is more addition because of OCS3. Fine, everyone? Okay, what's the
Yes.
answer for this?
So the first one is stated, right?
First one is greater. So you have direction like this, positive to negative like this. Both of them are oriented in the same direction. Positive to negative in this direction, positive to negative in this direction. So there will be some cancelling happening, right? So first one is greater. Absolutely right. Yes. Next. H2O and D2O.
E2 is greater, right?
And that's right. Positive to negative in this direction. And deuterium is having greater plus psi when compared to hydrogen. Okay. Plus psi of deuterium is greater than hydrogen. Okay. That being the case, you will have this to be lesser than this. Or I can say D2O is, what do I mean by this? D2O is more polar, right? Everyone, D2O is more polar than H2O. So D2O being more polar, can I say attractive forces among D2O molecules will be higher when compared to H2O molecules. Hence, if you look at the boiling point of D2O is 106 degrees, is around 106 degrees. And boiling point of H2O, we know that as 100 degrees, right? So greater boiling point is because of greater attractive forces among the D2O molecules. And boiling point is also dependent on molecular weight. More the molecular weight, boiling point is usually higher. Greater the molecular weight, greater is the boiling point. So with respect to molecular weight also, I can say D2O will be having greater boiling point. But the better way of saying it is D2O is more polar, hence boiling point is more. Everyone with me?
Yes.
Similarly, NH3, if you have lone pair is considered as higher density. So positive to negative will be in this direction. Here positive to negative, positive to negative. All of them are oriented in the same direction. That is, or they are oriented towards up. Here also it's the same thing, but D bond then will be having greater dipole moment because of greater plus psi effect of deuterium. So this will be lesser than this. Fine. Can I go ahead?
Sir, can you explain that NO2OCH3 part alone, sir?
NO2OCS3 part. In case of OCS3, you have a plus sum effect. Because of plus sum effect, the partial positive charge on OH3 will be more, even more significant, right? The partial positive charge on CS3 is due to hyperconjugation of it. The partial positive charge on OCS3 is due to resonance. Resonance is more dominating effect. So this will be having greater partial positive charge when compared to this.
Oh, okay, sir. Thanks, sir.
Okay. So you have greater charge separation. You have more of negative here, more of positive here. So greater dipole moment.
Hmm.
Okay, next question, everyone. NH3 and NF3. Everyone solve these questions. Again, I will give you some set of questions. You solve, we will discuss. Yes.
The similar dipole moment only, no, sir?
Yes, dipole moment, comparison of dipole moment. Shall we discuss, everyone?
The last question, sir.
Okay.
Sir, despite Cl participating in resonance, should we consider mainly inductive effect for the last question?
Yes. Okay, I'm discussing, everyone. So the lone pair nitrogen bond will be having the direction of dipole moment in this. Here also it is in this direction, positive to negative, positive to negative, positive to negative. So all of them in a way are oriented towards up. In this case, the positive center is the nitrogen and fluorine is the negative center. So you are having these three dipole moments in the opposite direction as the top lone pair, right? So there will be some cancellations. As a result, net dipole moment in NH3 is greater when compared to NF3. Okay. Second question answer. H2O OCH3, or you have methanol and you have ether.
Sir,
Yes.
B is greater than C. C is greater than B is greater than A, sir.
Yes, sir.
C greater than B greater than A. Yes. How many of you feel C greater than B greater than A? Please raise your hands. C greater than B greater than A. Okay. Okay. Okay, everyone. C greater than B greater than A. If I'm asking this question, what will be the answer?
A greater than B greater than C.
Yes, the answer is A greater than B greater than C. Everyone, the reason for it is, concentrate. You have the dipole moment pointed in this direction, positive to negative, positive to negative. Lone pairs, I'm not considering that because in all the cases you have lone pairs anyways. What's happening is you have CS3, you have two CS3 here. CS3 being a bulky group, in order to minimize the repulsive forces between CS3 and hydrogen, the bond angle increases. There will be increase of bond angle. The bond angle in this will be higher when compared to the bond angle in this. And the bond angle of ether is further higher. Okay. I am talking with respect to bond angle. This is not dipole moment direction. It is the bond angle. The bond angle increases because of the bulky group. So whenever the bond angle is increasing, if you look at the directions of the dipole moments, they will cancel out, right? Some part is going to cancel out, right? Because both of them are in opposite directions. If the bond angle increases, if it is 180, it will cancel out completely. If it is anything less than that, the cancellation will be there, but there will be some cancellation, effective cancellation. Agreed? So in this case, the cancellation will be much higher, followed by this, and there is no such cancellation happening here.
Sir,
Hence,
my doubt is that since CH3, despite being a bulky group, considering O to be a functional group, it can undergo hyperconjugation, no, sir?
hyperconjugation, you have already lone pair. Lone pair means two electrons in the orbital. You cannot have electrons shifting here. There is no hyperconjugation. There is only inductive effect in this molecule. There is no resonance also.
Okay, sir.
Okay. The bond angle is increasing, hence mu decreases, everyone. The bond angle increases, mu decreases. Because of the presence of the bulky group, the bond angle is increasing. Everyone with me?
Yes, sir.
If that's the case, everyone, this will be having the least dipole moment. The last one is having the least dipole moment, or mu equals to 0. Because if you have sp hybridization, proper hybridization without any lone pair, and if all the side atoms are same, then what is the dipole moment? It is net dipole moment is always 0. Right? In the other cases, what is going to happen? Even though you have 3Cl, even though you have 2Cl, the one with single Cl only is having the highest dipole moment, because if you have 2Cl, again, these two are two bulky groups. In order to minimize repulsions, the bond angle increases. So there will be some cancellations happening in the dipole moment. If you have three bulky groups, you will have even more bond angle happening. So there will be greater cancellation of dipole moments happening in here. Or the net dipole moment order is very important. CS3Cl is greater than CH2Cl2 greater than CHCl3. We may expect CHCl3 to be higher when compared to CH2Cl2 and CH3Cl. Having 3 C bond Cl, we may expect that to be higher. Understand the reason. The bond angle increases. As bond angle increases, mu decreases. Everyone with me?
Yes, sir.
Anyways, fourth one is mu equals to 0. So any of these three things will be greater than that. Last question, you might have got the answer. Carbon Cl bond, minus I is more dominant, so it is in that direction. This is in this direction, but in here it is in this direction. This is also in this direction. So this will be lesser when compared to this. Right? Okay. Very important note with respect to dipole moment. I will leave you after this. Everyone. Important note. If you have a para isomer with, in general, I'm taking two similar groups, but they need not. If they are not similar, obviously the net dipole moment won't be 0. And if you have a trans isomer or if you have a conformer, and if I take anti-conformation, you have a group here, which is responsible for the formation of a polar bond. So those groups are responsible for the formation of polar bond. What are the three things I'm taking? Trans, and then, sorry, this is para isomer, right? Para disubstituted benzene, a trans alkene, or an anti-conformer. If it is an alkane, an anti-conformer. First point, if G equal to any of the groups, whatever I'm mentioning, halogen, CH3, or CX3, or NO2, or CO minus, or C triple bond N, you can have more of them similar to these things. What do I mean by similar to these things? I will explain, you'll understand. In all those cases, mu resultant is going to be 0. If G equal to groups like OH, OR, SH, SR, COOH, COOR, or COCl, in a way which are not a symmetrical group, which is not a symmetrical group. If you observe, these are symmetrical groups. Okay, NO2, if you mark the structure and if you mark the resonance hybrid, it's a symmetrical thing. CO minus is also symmetrical thing. C triple bond and symmetrical in the sense it will be linear thing. Okay. All the other things, whatever I'm mentioning, they're not symmetrical. CH2Cl or CHCl2, etc. In all these cases, we may expect mu to be 0, but mu won't be equals to 0. Everyone. I will explain one thing now. The remaining of the things I will explain in the class. I'll end the lecture. If you have OH, if you have O bond H, something like this. If you have O bond H, the dipole moment because of this bond is in this direction, because of this bond in this direction, they may cancel. But if you have the same structure, you have free rotation about the sigma bond, no? So that particular OH can also be oriented, both the OH can be oriented in the same direction. You have something like this. In this case, O bond H is this side, O bond H is this side. So there may not be any cancellations. Okay, there will be some percentage of this because they are free rotation. You have conformations. You don't have all of the molecules appearing in the same way. You can have these as well. So the net dipole moment won't be 0 of the molecule. Agreed. So whenever you have asymmetrical things, you won't be having, or wherever you have free rotation, you may not have cancellations. Right?
Yes, sir.
If you have the CX3, the net dipole moment will be in the one direction. The other case also net dipole moment will be in the direction, no matter how you rotate it. If you have C triple bond, then it's a linear thing. C triple bond then is linear. So it's always oriented in one specific direction. You always have C triple bond N here. No matter how you rotate around the single bond, it is going to be linear only here. So it's always oriented in one direction, there will be cancellation. That the net dipole moment is going to be 0. Similarly, we can explain for this trans part as well as this anti-isomer. If it is anti, this is oriented in one direction, another direction, it may cancel out. But if the group is not symmetrical, if it is having some different orientations, one orientation may cancel, another orientation may not cancel. Okay, we will talk more about this in the lecture tomorrow. We will talk more about this in tomorrow's lecture. I will give examples as well. I am ending the lecture now. I have another lecture at 3 o'clock, so I am ending it right now.